Hello, everyone. Welcome back. And it's a great pleasure to welcome Jacob Matherne, who will be talking about singular Hodge theory. Take it away.
Yeah, so thanks. I just want to say that this is the part one. There are two talks in this series. The next talk will be next week, but 1 hour later than the usual time for this seminar. So the idea is that we introduce some kind of intersection cohomology theory for matroids, and my talk and Nick Proudfoot, who will be talking next week, we're each talking about one of the applications of this theory. So my application is a proof of some conjecture from the 70s. It's completely combinatorial, called the Top-Heavy Conjecture. And Nick Proudfoot will talk maybe more about something that is kind of something that's might be known to this audience, at least with respect to the classical Kajan-Lustig theory and stuff like this. So he'll talk about Kajan-Lustig polynomials for matroids, and his application will be that they have non-negative coefficients. So good. There are two papers in case you want to look. The first one is sort of the main one, and the second one is, well, the main one relies on the second one. So yeah. So this is joint work, like I said, with Tom Braden, Jun Huh, Nick Proudfoot, and Botong Wang. So here's the outline. So first I'm going to tell you what this top-heavy conjecture is. And then this is something that makes sense for all matroids, but all of my examples are going to be sort of very concrete in terms of hyperplane arrangements. And when you have hyperplane arrangements, you have all of this geometry, and you can prove this top-heavy conjecture using topology and geometry. And I'm going to tell you about the proof of this in 2017 due to Jun Huh and Botong Wang. But as I said, you can state this top-heavy conjecture in general for all matroids, and our contribution was to prove this for all matroids when you don't have any geometry to rely on. And I'll tell you about that in the third section. Okay, so I'll try to keep it very elementary. So let's start. So part one, I'm going to start with a vector space. I don't care about what field it's over. And A is going to be a finite set of hyperplanes inside of this vector space. With the property that if I intersect all of these hyperplanes, the intersection of all of them is the origin. So let me give you a definition. I want to start intersecting these hyperplanes and see which subspaces of the vector space I get. So a flat is any subspace I can get by intersecting the hyperplanes. Any subspace obtained by intersecting some hyperplanes. And I'll do an example now. So the first example, I'm going to have a two-dimensional vector space. So I'll draw a plane. And I'm going to have three lines. So I have three hyperplanes inside of this two-dimensional vector space. And these lines will be intersecting in the origin. The intersection of all of them is the origin. So I have hyperplane 1, hyperplane 2, hyperplane 3. Okay, so I want to organize the information of these flats inside of a poset. Okay, so I'm going to start intersecting these lines. So this poset I'm going to get is going to be called the lattice of flats, or hyperplane arrangement, people call this the intersection lattice. And here's what it is. So if I intersect none of these lines, none of these hyperplanes, I get the vector space I start with. If I intersect any one of the lines, that's just the line itself. So I have hyperplane 1, hyperplane 2, hyperplane 3. So far I haven't said anything interesting. And now, so if I intersect two of the lines, like H1 and H2, then I get the origin. Okay, so I'm going to add that subspace in. And now if I intersect three of the lines, I still get the origin. So there are no new subspaces that I can get. So these are all of the flats, all of the subspaces I can get by intersecting the hyperplanes. And this is a poset, and it's ordered by reverse inclusion. So the origin is contained inside of each of these lines, and each of these lines is contained inside of the vector space. And it's a ranked poset. It's ranked by the codimension of these subspaces. So the codimension of the vector space is 0, 1, 2. Okay, so it's ranked by codimension. And let me just have some notation here. So the set of all flats of rank 0 or codimension 0, I'm going to write L superscript 0, L superscript 1, L superscript 2, and so on. Okay, so the top-heavy conjecture is going to be some statement about the shape of this poset. Okay, and this poset is so symmetric that it doesn't really say anything interesting in this example. So let me show you sort of a more interesting example. So here is a lattice of flats, and this is what I get when I have 4 planes in 3 space with the property again that the intersection of these 4 planes is the origin. Okay, so let me just explain. So here's the 3-dimensional vector space, and then I have my 4 planes, and if I intersect 2 of the planes, I get like the plane H1 and H2, I get this line, which I write H12. So H12 is the intersection of this plane H1 with the plane H2. Okay, so I can intersect these planes in all possible ways, and I get 6 lines. And now if I intersect 3 of the planes, I get the origin. Okay, so this is my lattice of flats in this case. And now I'm going to tell you what this top-heavy conjecture says. It says that if I draw a horizontal line through the middle of this poset, and I start at the top of the poset, and I go down some number of levels, but don't cross this green line that I drew, and then start at the bottom and go up the same number of levels, then there are more flats at this level than this level. Okay, so in this picture, I can compare sort of this level and this level. And this says that 1 is greater than or equal to 1. Okay. And I can also compare this one with this one. And this says that 6 is bigger than or equal to 4. So the top-heavy conjecture says that I'm always going to have sort of more things on top in the complementary degree. Okay. So let me write this down. So the poset is in some sense top-heavy. Okay. So the top-heavy conjecture this was a conjecture by Dowling and Wilson in '74. And it says for every k less than or equal to 1/2 the dimension of the vector space. So this is saying that I can't cross this green line that I drew. The number of flats of codimension k is less than or equal to the number of flats of dimension k. Okay. So as I said at the beginning, this was proven by 43 years after the conjecture was made by Huh and Botong Wang. That's in 2017. In the case of hyperplane arrangements, which is all I've talked about so far. But this conjecture makes sense for arbitrary matroids. See, a matroid has a lattice of flats, and it has a rank function. So you can ask this question: what is the shape of this poset? And this is what we prove. Braden, me, Proudfoot, Wang. This is in 2020. So this is for all matroids. Okay. So let me just mention that there's a strengthening of this, which we can also prove. This can be non-symmetric. See, the way I stated the top-heavy conjecture is that I go down some number of levels and I compare it to the complementary rank, right? So there's some symmetry here. But I don't have to be so symmetric. So what I mean precisely is that I could delete this and instead replace it with, for every k less than or equal to j less than or equal to the dimension of the vector space minus k. And then I compare flats of rank k to flats of rank j. So what I mean is I pick a top line, I pick a bottom line, but I keep this bottom line the same. And now I can compare the number of flats at this bottom rank to any of the ones in between up to the complementary rank. Okay, so there's a non-symmetric statement like this. Because this crowd is probably more familiar with Coxeter groups and stuff like this than matroids, let me tell you about some top heaviness that appears in Coxeter groups with the Bruja order, before I go on to talk about the proofs. So if W is a crystallographic Coxeter group, and I'm going to use F sub I super W to be the number of elements of length I below W in the Bruja coset. Okay? Then there's a paper by Bjorner and Ekkedal in 2009. It's called On the Shape of Bruja Intervals. That says basically the same thing as what I just wrote for the top-heavy conjecture. It says for every k less than or equal to j less than or equal to the length of W minus k, the number of elements of length k less than below W is less than or equal to the number of elements of length j below W. So if you pick an element and look at the lower interval, then this is top heavy. And there's a paper that hasn't appeared yet, but these guys have been working on it for some time now, and I've seen the preprint. So this is by Melvin and Slofstra. So they use Zirkel bimodules to remove the word crystallographic. Okay, so I don't think that's on the archive yet. Okay, so now let me just tell you about the proof in the case where we have hyperplane arrangements. So we can prove this geometrically. Any questions, or do you not take questions until the 5-minute break, or do you?
No, we take questions, but everything's crystal clear.
Yeah. Please ask me questions. Everybody understand the statement of the top-heavy conjecture? Okay. Okay. So again, this is due to Huh and Wang. So hyperplane arrangements, when I talk about matroids, these are what are called realizable matroids. Okay. So I have this vector space V that I started with that my hyperplanes live inside. There's some chat. Okay. So the numbers don't increase to the middle and then decrease. They increase to somewhere and then decrease. Yeah. Okay, so I have my vector space V, and I can consider the quotient map where I just quotient by one of these hyperplanes. Okay, and now I'm going to sum all of these quotient maps. And remember that I'm assuming that when I intersect all of the hyperplanes, their intersection is the origin. So that means when I sum all of these quotient maps, I get an injection. Okay, so now, well, hyperplane is something of codimension 1. So this is isomorphic to a bunch of affine lines. And now what I'm going to do is maybe a weird thing. So I'm I'm going to add a point at infinity for each one of these affine lines. Okay. So I'm not going to embed this inside of p to the n. I'm going to embed it inside p1 to the n, where n is the number of hyperplanes. Okay. So here's the first object that when Nick talks next week about the Kazan-Lustig theory of matroids, this is sort of the first object that is playing a role in this Kazan-Lustig theory that's analogous to something for flag varieties and Coxeter groups. So I'm going to define something called the Schubert variety of a hyperplane arrangement. And it has the name because it plays a similar role. So this is, what I do is, I'm going to call it y sub a, and it's going to be along the sequence of maps, I'm going to take the closure of V inside of this product of P1s. Okay, so let me give you some idea about what this looks like. So remember in the first example, we had these 3 lines inside of this 2-dimensional vector space. And this Schubert variety of the hyperplane arrangement in a neighborhood, in an affine neighborhood of the origin, it's just going to look like the vector space V that I started with. And sort of on the other end of the world, in the neighborhood of infinity, 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 this is, by the way, the most singular point. It's going to look like an affine cone. So this is the point infinity, infinity, infinity. Okay, let me tell you more about what this looks like. So another thing that happens in the classical setting and sort of flag varieties is you have stratifications by affine spaces. Okay, so our variety Y, our Schubert variety, has a stratification by affine spaces as well. Okay, so let me say a little bit about the stratification. So I dropped the subscript A because I'm never going to talk about 2 different hyperplane arrangements. So I have a hyperplane arrangement A, and then it produces for me a variety Y, a Schubert variety. So I'm calling that Y now. So it has a stratum for each one of the elements of my poset, for each one of these flats. And here's a definition of the stratum. So it's the points such that the one with coordinate for the hyperplane H is not infinity if and only if the flat that's labeling this stratum is contained inside of this hyperplane. Okay, so let me give you the 2 extreme examples. So if at the very bottom of my poset, I have the whole vector space V. And so the vector space V is not contained in any of the hyperplanes, right? So that means all of the coordinates are infinity. So it means that this is maybe equals. And in general, I guess, it continues. And then at the other end, the top of the poset, I have the origin. And this is the other way around. Now, all the coordinates are not infinity. So this is the vector space itself. Okay, so there's another way to describe this. So the vector space V acts on itself by translation, by adding elements. And these strata are orbits for this action. Okay, so this is V mod F. So this is the V orbit with stabilizer F. Okay. So that's all I'll tell you about the stratification. But here is a consequence of having a stratification by affine spaces. So when you have, now what I'm saying has nothing to do with this variety Y. When you have a stratification by affine spaces, I have that are labeled by the flats, I have the cell decomposition. So in this case, the dimension of the 2k degree cohomology of my Schubert variety is the number of elements of my poset of rank k. Okay, so it has no odd degree cohomology. This is the even cohomology. And in this paper that I told you about before, this paper called On the Shape of Bruja Intervals, so they weren't studying these Schubert varieties for hyperplane arrangements, but they prove a general fact that says that if you have a stratification by affine spaces, then the singular cohomology of whatever variety is stratified by affine spaces injects inside the intersection cohomology of the same variety. Okay. So this will be important for us. Okay, so why am I telling you all this geometry? Let's remember what we're trying to do. We're trying to prove the top-heavy conjecture, which is a statement about the number of flats at some level compared to is less than or equal to the number of flats at the complementary degree. That's the symmetric statement. And I have the cell decomposition here, which these were the numbers I was interested in. I wanted an inequality in these numbers. So that means that I want some inequality on the dimension of these degrees of cohomology of the Schubert variety. So that means I can prove an injection between two different degrees of cohomology of the Schubert variety. So let me say what I mean. So I wanted to show that the number of flats of rank k is less than or equal to, let me give myself some more space here, is less than or equal to the number of flats of rank, the dimension of the vector space minus k. But using the cell decomposition here, here's what would imply that. The dimension of this vector space is equal to the left-hand number, and I can look at the dimension of this vector space, and I want these one dimension to be smaller than another one, so I want an injection here. That would imply this top-heavy conjecture. Okay, so I would have such an injection. This is called the Hard-Lefschetz theorem, if Y were a smooth projective variety. But it's not. I sort of showed you here, at least in this example already, it's singular. Okay, so that's why we're going to make use of this intersection cohomology here. So intersection cohomology sort of satisfies a lot of the same properties that singular cohomology does, but for singular varieties instead of smooth ones. Okay. So how are we going to prove this? So we need an injection. So I'm going to take an ample class. And again, if my k is like it was in the statement of the conjecture, it's less than or equal to 1/2 the dimension of the vector space. Then I can set up the following diagram. So Bjorn and Ekkedal tell me that the cohomology injects inside the intersection cohomology. So this is this Bjorn or Ekkedal inclusion. And I also have it up here. Okay, and then the Hard-Lefschetz theorem for intersection cohomology, well, this Y is singular, but it's a singular projective variety, so I have the Hard-Lefschetz theorem for intersection cohomology. So it says that if I multiply, so this L, if I multiply by this L enough times, so dimension of V minus 2K, then I get an isomorphism here. Okay, so this is multiplication by this ample class. Okay. And what I'm going to do now is I'm going to restrict the multiplication from intersection cohomology to cohomology. So this is the same map where I multiply by L some number of times, the same number of times. And now it's just this diagram commutes, and it's just a formal statement about commutative diagrams when I have an isomorphism and two injections. If I have an isomorphism and two injections, then that means that this must be an injection. Okay. So this implies the top-heavy conjecture for hyperplane arrangements. Okay. So this was the proof of Huh and Wang. So, okay, maybe I'll talk for a few more minutes. I'll set up the setting for arbitrary matroids, and then we can pause for questions. So now, the third part of the talk is I have this top-heavy conjecture. It makes sense for arbitrary matroids. Oh, before I get there, let me talk about this this strengthening up here. So remember, I had this non-symmetric strengthening. So this follows immediately because, like, okay, so the symmetric one I just proved for you. When I multiply by this ample class enough times, I get an injection. So I compose the map with itself a bunch of times, I get an injection. So the non-symmetric statement says I just compose the map with itself fewer times. So it's still an injection. Okay. Okay. So as I said, this top-heavy conjecture makes sense for all matroids. So what I mean is, I'm not going to say what matroids are, but I'm going to tell you that the definition of a matroid is that you have a lattice of flats. You have some lattice that of subsets of a finite set satisfying some axioms, which are, these axioms are made to generalize the axioms for that we have flats for hyperplane arrangements. Okay, so they have a lattice of flats, and it's a ranked lattice. So there's some poset. It has a rank function, and you can ask the question about the shape of it. Okay, so all I need to know is that I have such a thing, and I can ask about its shape. But what I do want to tell you is I want to explain, like, what is the difference between, so I just gave a proof for hyperplane arrangements, which could be called realizable matroids. I want to tell you how big is the gap between realizable matroids and all matroids. Okay. So, but most matroids are not realizable. Even though the definition is very much inspired, it just axiomatizes what happens for hyperplane arrangements. It axiomatizes all kinds of other things that happen for all kinds of other things too, like graphs and you know, linear independence and vector spaces and so on and so forth. So even the definition comes from this, but there's a big gap between the realizable ones and the non-realizable ones, or all of them. So let me make this precise. So I'm going to let Rn be the number of realizable matroids with n elements. So you should think of this as like hyperplane arrangements with n hyperplanes. Okay. And Mn is just going to be the number of matroids with n elements, not necessarily realizable by a hyperplane arrangement. Number of matroids with n elements. Okay. Then there's a theorem by Peter Nelson in 2018 that says that if I take the ratio of the number of realizable matroids on n elements to the number of matroids on n elements, and I let the number of elements go to infinity, then this is 0. So this is what I mean. This is kind of a precise statement that most matroids are not realizable, at least in this limit. Okay. So I'll talk for 4 more minutes. Okay, so the goal is I want to prove this for all matroids. And what I'm going to do is I'm going to sort of emulate this same proof. I'm going to set up some kind of commutative diagram like this. I'm going to have some ample class, and I want to use the Hard-Lefschetz theorem. Okay. The problem is that for arbitrary matroids, well, I don't have this hyperplane arrangement. So I don't have the cohomology of this hyperplane arrangement. So I don't have the intersection cohomology of this hyperplane arrangement. I really don't have any geometry at all. Okay. So what I want to do is, well, when I don't have a hyperplane arrangement, what I want to do is make some kind of combinatorial stand-in for all of the objects in this commutative diagram. Okay. That makes sense just in terms of this poset, because that's all I have. So the goal is going to be to find combinatorial replacements for the cohomology of the Schubert variety and its intersection cohomology. Okay. So I'm really trying to not steal Nick's thunder here. Like it's a there's a lot of things I want to say, but yeah, it's like the cohomology of the flag variety and so on. All of this we're basically studying Zergel modules or something like this. Modules. I mean, this intersection cohomology is going to be a module for the cohomology of the flag variety, but it's going to be making sense for any matroid. Okay, so let me first tell you about this cohomology of Y. How do I define this for, Nick is here, still away. Thought you're supposed to be teaching. Okay, so, okay, so let me tell you about the combinatorial stand-in here. So the graded Möbius algebra of M is, so as a graded vector space, I just have a generator for each element of this poset. So I'm writing L of M now because it's the lattice associated to the matroid M, but you should think of L of A, the same thing I was writing before. And I'm going to place this guy, its degree is the rank of the flat. Okay, and now it's an algebra. Let me tell you what the multiplication is. So the multiplication is very simple. So if I multiply two of these guys, I get the generator for the join in the poset. So it's the smallest thing that's above both of these in the poset. If the rank of F plus the rank of G is equal to the rank of the join. And otherwise it's just 0.
Is the join like the intersection of the hyperplane of the subspaces?
Yeah.
Okay.
That's right.
It's annoying that it's the other way.
Yeah, this is always, yeah, I know. Yeah, I always forget the symbol. That's right. Yep. We're fighting a long, long history of notation here. Yeah. So here's a theorem in the same paper that proves the top-heavy conjecture for realizable matroids or for hyperplane arrangements. They prove that this graded Möbius algebra is isomorphic, and you have to do some degree doubling here because this has no odd degree cohomology. So I'm going to write y sub a here because I want to say this is true when this arrangement realizes the matroid. So when it's a realizable matroid with this hyperplane arrangement A. Okay, so I have a combinatorial stand-in for the cohomology of this Schubert variety. And then maybe, yeah, maybe this is a good place to pause. I think this is about 35 minutes. Yeah, so what I'm going to do next is talk about what the combinatorial stand-in for the intersection cohomology is.
Thanks, Jacob. So we'll come back in 5 minutes at 1:41, but if anyone has questions, please ask.
Yeah, I'll be here.
Does it make sense to consider covariant cohomology? So there is some torus action which scales everything.
Yes. So yeah, Tom Braden has been thinking about this quite a bit, and yeah, I remember when we first started talking about thinking about this. One of the things that made Tom unhappy was that there's only a C star acting in general on this Schubert variety Y. You can do a lot with this, but there's really not a higher dimensional torus. But yeah, you can consider equivariant cohomology, but with just a C star. These things are not toric varieties.
How much do we understand about unrealizable matroids? Like, is there a classification theorem for them?
Well, so you could ask. So here's an answer, and tell me if it satisfies you or not. So I mean, I defined matroid, or I didn't define matroid, but I said that a definition of it is in terms of its lattice of flats. So there's an axiomatization of like which lattices come or the lattice of flats of matroids. So these are called geometric lattices. So like if you give me a lattice, I can decide whether it is the lattice associated to a matroid or not. So yeah, and this has nothing to do with realizable or not.
Yeah, there's no axiom. Sorry. There's no axiomatization of what it means to be realizable, though.
Yeah, that's a good question. Yeah.
That's sort of a famous question, and there are a couple of papers written in response to that question called, you know, "The Missing Axiom of Matroid Theory is Lost Forever" or something like that. I mean, you know, Whitney defined matroids, and he considered it sort of a failure of the definition that it was allowing in all these non-realizable examples, and he was like looking for the extra axiom that would rule them out. And at various points, people have published papers that say if you work within the following, you know, logical framework, there does not exist an axiom. You know, there does not exist a logical sentence of the following form, you know, which rules out exactly non-realizable matroids. And then a couple of years later, like, well, actually, that was a lame hypothesis, but there doesn't even exist a sentence of this form that rules out non-realizable.
So, yeah, it goes on, yeah.
But I mean, eventually the community has come to believe that, in fact, the Whitney's definition of matroids is the most natural one, and one shouldn't be ruling out non-realizable ones.
Did you have more of that question, Jaden?
I have a question. So this, so if you choose L and then you consider all these towers of like powers of L, so do you get interest in filtration cohomology by like saying from which, what is kind of the image of L, the image of L square, basically the image of L cube and so on. So this gives you an interest in filtration on the whole cohomology?
Mm-hmm.
Is it considered anywhere in this business?
The Lefschetz filtration, you said?
Yeah, kind of Lefschetz filtration, yeah. I mean, it's kind of Jacobson-Morozov filtration for L, I guess, if you want.
Yeah, I don't think we think about that. Am I right, Nick?
Wait, so that's kind of going to be the subject of my, wait, so let me make sure I understood correctly. So one thing that we do think about that I'll talk about next week is you take like, you know, H2K of Y modulo, sorry, IH2K of Y modulo H2 times IH2K minus 2.
That's slightly different. No, what I'm asking is just like a fixed L, like one fixed class in H2, and then you have the image of L, like whatever you get by multiplication of L. Then you have the image of L square, which is contained in that, and the image of L cube, which is contained in that. And so this gives you filtration, and it's a filtration on H cohomology group.
Right. So we
And-
don't think about it for a fixed L. We think about it for
we think about it for sort of all of the elements, these y's that generate this h.
Mhm.
Right. So instead of thinking about multiplication by L, think about just multiplication by the entirety of H2. And then it turns out to be very interesting.
Right, because H2 is very large in this case. I see.
Yeah.
It's like the number of hyperplanes. I see.
Exactly.
Yeah, this is really, I guess, Nick will talk about this, but this is, looking at this filtration is really a key point in proving this non-negativity
Mhm.
of the Kazan-Lustig polynomials.
Okay, that's Jin, did you want to finish your question? Do you have more?
Kind of, yeah, just a continuation. So can you provide a brief idea of how the theorem by Nielsen is proved?
Oh, geez, I don't know. Yeah, I haven't looked
Okay.
at this paper. No.
Fair enough. Thanks.
Okay,
I've looked at it, but it's not simple. It's just very, very delicate, analysis.
okay, let's continue.
So should I do 15 minutes from now?
Sounds good.
Okay, sounds good. Okay, so now I want to talk about what is the combinatorial stand-in of intersection cohomology. But sort of it's hard, at least for us, to give a presentation of intersection cohomology. Like here, they had this graded Mobius algebra for the singular cohomology of the Schubert variety, and everything is a very nice and easy algebra to define. We don't know how to do this for intersection cohomology. So what we're going to do is we're going to find something bigger that is easier to describe. So we have some explicit resolution, and since Nelson, since Nick said that it's okay to steal his thunder, this is like a Bott-Samuelson resolution, okay? And it's canonical, so it doesn't depend on like a choice of reduce word. So it's really a canonical thing. That's a difference with the Bott-Samuelson resolution. So what we do is we blow up the point. So this is the stratum corresponding to the vector space, which is the stratum is the most singular point, infinity, infinity, infinity. And then we blow up the proper transforms of the closures of the strata one dimension up. For all F that are rank 1. And we continue doing this all the way up. Okay? So let me tell you a definition. So there's this thing called the augmented Chow ring. And it's called augmented because there's something already called the Chow ring of a matroid. And it's related, but not the same. So this is the graded ring. So what I'm about to define is going to be the cohomology of this resolution, okay? But it's going to make sense for any matroid. So maybe I'll go down here. It's going to take some space. So I have a generator, so I have some X's and some Y's, okay? So the X's are labeled by proper flats. So every one except the top of the poset. And the I's, so maybe I'll write it like this. So E means the ground set of the matroid. It means like the number of hyperplanes, okay, the set of all hyperplanes. So this E is the ground set. It's called the ground set of the matroid. Okay, so we have some X generators, one for each proper flat, and we have some Y generators, one for each flat, one level up. Okay, and we have the following relations. So if I multiply two of the X guys, I get 0 if the F's, if the labels of them are incomparable inside the poset. Okay. one of these y's, it's defined to be the sum of all the x's that don't contain I, where their label doesn't contain I. And I have this last relation that's yi times xf is 0 if I is not in the flat F. So this is called the augmented Chow-ring of a matroid. It's something you can work with. And the theorem, as I said, this is something we prove in our paper. That this is the cohomology of the resolution when we have geometry, when A realizes M. Okay. So
can I ask about some of these elements? Like,
yeah.
So in the normal homology, you've got elements yi, one for each rank 1 flat for each hyperplane.
Yeah, inside this guy, yeah.
And they because you can define all the other flats as products of these.
Yes.
What's the what relations then do you impose to get the normal homology? Like, what's that?
Yes. So here, I don't know if this is an answer to your question, but let me say something. Okay, so I'm actually going to say this in a moment, but I think I can say it now. So this embeds inside of here. The graded Mobius algebra embeds inside of here. And it's just the subalgebra generated by the yi's. But I could take so I can take one of these y sub f's, these generators here, and I can send it, here's the map, I send it to a product of yi's where I want to take all the i's in a basis of f. And it doesn't matter what basis you choose. Okay, so this gives me an inclusion of the graded Mobius algebra inside the augmented Chow-ring. Does this answer your question?
So the fact that it doesn't matter what basis you choose is somehow because of that second relation or something?
Yes, yeah, you have, right. Yeah, you just have to play with these relations. That's right. Mm-hmm.
And these blow-ups, like I'm trying to figure out how I should think about XF, because you blow up along each flat. Does XF come from that?
Yes, exactly. Mm-hmm. Yeah, so when you blow up the point, you add in X empty, and so on. Yeah, that's right. Yep. Good. So I'll just say this. I don't know if anybody is familiar, but the Chow-ring of Adiprosito, Huh, and Katz is the cohomology of the pre-image of the most singular point along this resolution. So it has a similar presentation. Okay, so now I have combinatorial stand-ins that make sense for all matroids for cohomology and intersection cohomology. So, well, not quite intersection cohomology yet. So I have it for cohomology and then the cohomology of this resolution, right? So let me tell you the strategy of the proof for the top-heavy conjecture for all matroids. So I still need to get at intersection cohomology. So sort of what I do is geometrically, this is the picture. I have the cohomology of the Schubert variety, and this is inside the intersection cohomology. This is this Björner-Eckedal thing. And then this is inside the cohomology of the resolution. Okay. And then I understand this is the graded Mobius algebra. It makes sense for any matroid. And this is the augmented Chow-ring. This makes sense for any matroid. And now I need to see what the intersection cohomology. So what I should do is I should decompose this augmented Chow-ring as a module over this graded Mobius algebra and find a nice sum n and call that the intersection cohomology module. Okay. So here's what we do. So this, I guess, is what I just, the answer to Ben's question that I just described. So the augmented Chow-ring contains the graded Mobius algebra as a graded subalgebra. via this injection up here. So now, okay, so H of M acts on it, and I'm going to decompose it. So decompose the augmented Chow ring as a graded module over the graded Mobius algebra. Okay. And here's a cheap way to define the intersection cohomology just by using the Kroll-Schmidt theorem. Okay, so it's the correct thing, but it's not useful to prove theorems. So Kroll-Schmidt says that, I mean, I can define it up to isomorphism. There exists a unique, indecomposable, graded H of M module, direct sum n. I'll call it IH of M, that is contained inside of CH of M and contains H of M. Okay, so this is some definition up to isomorphism, so it's not a canonical definition of the intersection cohomology. So I'll say a little bit at the end about we define it better canonically, and this is what we use. So now that we have this intersection cohomology of a matroid, defined as some direct sum n in this decomposition, I mean, all of these steps take quite a bit of work, but I'm just saying what we have to do to make this commutative diagram work, right? So we prove the Hard-Lefschetz theorem for this intersection cohomology module. And then we use the same commutative diagram as before. And the ample class is a sum of positive constants times yi's. Okay, so all of this implies the top-heavy conjecture by just doing the same thing as before. So this is with Tom Braden, Jun Huh. It's myself, Proudfoot, and Wang. So this is top-heavy for all matroids. So let me just say a little bit more, and I have 3 more minutes, it looks like. So I want to make a few more remarks on this proof that I guess I've said some of them already, but I want to write them down. So the definition of the intersection cohomology module of a matroid that we give in number 2 here using the Kroll-Schmidt theorem is not canonical. It's up to isomorphism. It's good for statements, but it's not good for proofs. So in 2 is not what we use to prove things. So what we do instead is we can write down a decomposition of this augmented Chow ring, a canonical decomposition of it. And we can use this canonical decomposition to define the intersection cohomology in a canonical way. So when we decompose the augmented Chow ring, we can really write down a canonical decomposition. We can write it down. So I mean, I would say that most of, I think I would say that most of the work of this paper is trying to study the decomposition of the augmented Chow ring as a module for the graded Mobius algebra. And sort of a deep study of that. So instead of this Kroll-Schmidt decomposition, we define this IH of M canonically, because we have a canonical decomposition. And the last thing I want to say is, in addition to hard Lefschetz is the only thing that we need for the application to the top-heavy conjecture. So in number 3, I said that we proved the hard Lefschetz theorem for intersection cohomology. It's the only thing we need for the application, and it's also the only thing Nick will need for his application, for the non-negativity of Kajan-Lustig polynomials. But we can't prove it alone. So as probably a lot of you know, you have to prove lots of other things all together in some big induction. So we prove Poincare duality in the Hodge-Riemann relations for each of them as well. And sort of all of these things are part of a very large induction. It's all part of a large induction, and everything has to be proven together. Basically, you can't prove anything alone. And it's not just this. I mean, I think there are, I don't know, 12 or 15 statements in this induction. Okay, so I think that's all what I want to say. Thanks.
Thank you, Jacob. Oh, where's the canned applause? Nicole's not on the ball. Usually we give canned applause.
Sorry.
Great. Well, we have a couple more minutes where we can bother Jacob with our questions. Thanks for the great talk.
Yeah, thank you for having me. Questions?
So why is Schubert calculus so easy in this setting?
Why is Schubert? What do you mean?
Well, I don't know. I feel like, describing the cohomology ring of Schubert varieties with its multiplication structure. Oh,
you're saying this is so easy, yeah. Right.
I'm just like, yeah, well, I guess why is it so nice?
Yeah, I mean, so these varieties Y have a lot of nice structure that I guess Schubert varieties don't. So I mean, this theory is both easier and harder and different. In some ways it's easier, some ways it's more difficult than the classical story. I mean, sort of geometrically, the Schubert variety is quite nice in the sense that if you take the closure of any of this strata, you get another Schubert variety for a different matroid or a different hyperplane arrangement. And if you take a normal slice to a stratum, then you also get another Schubert variety for a different arrangement. So it has sort of closure properties under lots of things. Yeah, and this is sort of very important for us. Maybe I'll stop my share and I can bring it back if anybody wants to look at anything in particular. I'll remove the spotlight.
Let me remove your spotlight too.
Yeah.
Do you have a smoothing of this Y? So can you embed it in some nice smooth family as well as resolving?
Can you embed it in a nice smooth? Oh, I see. Is there some parameterization where this is kind of the smooth guy?
No, where this is the central fiber. So the total space is smooth, and this is like the central fiber and the generic fiber is smooth. Like that.
Yeah, I haven't thought about that. Yeah. There are questions in chat. Okay. Yeah, cool.
Yeah, where does this canonical decomposition come from?
Yeah, so basically what we do, I mean, we figure this out just by playing with elements a lot. I mean, really writing down trying to, in small examples, trying to write down the module structure. But what you get is, I mean, the biggest thing is the intersection cohomology of the matroid. And then after that, you get contributions from smaller matroids. So you have a direct sum over all the flats, except the top one. And the contribution is the Giesen push forward of a tensor product of augmented Chow rings for the upper and lower intervals. So what the deal here is this, right? So geometrically, when you do these blowups, you have this resolution, and the exceptional fiber has a bunch of components, one for each stratum, one for each F in the lattice. And it has you can write down, it has a decomposition because of what I said, that the slice to a stratum and the closure of the stratum is also things of the same type. So you get a product structure. So you get a product of like an upper interval and a lower interval, and these two, you get the varieties of these two types. And that's why you have this tensor product of these augmented Chow rings. And then you use the Giesen push forward map to push it to the whole matroid.
As a module over the cohomology, like how does the cohomology act on this tensor product? It acts on on one factor, it acts on both, or
it acts on one factor, I believe. I mean,
and the others are multiple.
So there's a map from H of M to H of M for the upper interval that just kills some of the Y's. So it's a module for HM, but it just acts on one of the factors. Yeah.
Got it. So all the lower terms that you kill to get what you want, which is the intersection cohomology, these lower terms are all just many copies of intersection cohomologies of sub-matroids.
Yeah. So first they're copies of, augmented Chow rings for upper intervals, with some shift.
Oh, of the augmented Chow rings. So then those have summands. Okay.
But then those decompose in terms of those decomposes intersection cohomology of
right, of course.
For other matroids as well. Yeah. So somehow, I mean, but the coarser decomposition that I described to you in terms of these Giesen push forwards of tensor products of augmented Chow rings, that's sort of easier to prove than the full decomposition into sums of intersection cohomology.
Very nice.
We get that way later in the induction. In fact, like proving that this intersection cohomology module is indecomposable comes sort of, you have after you prove everything. I mean, you need the whole Kähler package before you can prove that it's indecomposable. So it never, I mean, you never know that it's indecomposable in the whole induction. You get it at the end.
Right, because you're not doing Kroll-Schmidt to say what's looking at indecomposable.
Yeah. So we define it using like, so we have these smaller summands that are Giesen push forwards for other matroids. And so there's a Poincare pairing on this augmented Chow ring. So there's a degree, so this augmented Chow ring in top degree, the top degree is the rank of the matroid. And it's one dimensional in that degree. And so there's a degree map, which is just it's an isomorphism to this one, to Q, which takes, it's, how do you define it? You take a maximal flag of X sub Fs, a product, X empty times XF1 times XF2, so you pick a flag in the post set and you multiply all the X generators in that flag, a maximal flag, and you send that to 1. So this is how you define this degree map, and this degree map gives to you a Poincare pairing. And now how we define the intersection cohomology module is we sort of define it inductively because all of these smaller summands depend only on smaller matroids. You can kind of assume what they are inductively. And then you define the intersection cohomology to be the perp.
The perpendicular, exactly.
To all of these with respect to the Poincare.
Very nice.
So that's the sort of canonical definition.
I've never thought about defining the indecomposable Zirkel bimodule as the perpendicular to all the other things. So that's a nice way to think about it.
Yeah, like all of this canonical decomposition, all the summands are orthogonal to each other, all the smaller summands as well.
Cool. Is this resolution semi-small? No. Like these other push forwards come with shifts.
Yeah, that's right. There is a thing that's semi-small, which is in the first paper. So I wrote two papers down. The first paper, I mean, I think the title has semi-small decomposition of the Chowdering of a matroid. So what we do there is here's a semi-small map. You take a Schubert variety for a hyperplane arrangement, and then you delete one of the hyperplanes, and you form the Schubert variety for that hyperplane arrangement where you've deleted one. Now you have a map from Y to Y for the
neither is smooth, but it's semi-small.
Yeah, right. And you can look at the decomposition theorem there, and that decomposes for you the augmented Chowdering as a module of the augmented Chowdering for the matroid where you delete an element. And this plays a role in this induction.
Of course. Do you get I guess probably from that, do you get relative hard left shifts?
Yeah, I don't know what relative hard left shifts is. So we have weak left shifts. I don't think we use, so relative hard left shifts I don't think comes into our, it's not one of the statements in our induction unless it's hidden.
Right. Maybe I should shut up for a second in case any of the other people still hanging around have questions. But I was thinking of turning off the recording. I'm going to thank you again on behalf.
Thanks, Ben.
Wait.
Oh, right.
Whoa, Nicole, what?
She's got it. You need to do it again, Nicole.
That was it. Thank you.
Okay.
That was what was supposed to happen. I'm sorry.
Thank you. How are you? Are you doing all right?
I'm doing very well. Thank